Welcome to today's paper reading. Today's paper is titled, RealGen, Retrieval Augmented Generation for Controllable Traffic Scenarios. This paper was published on AR14 by Wenhao Ding and colleagues from Carnegie Mellon University and NVIDIA Research. Simulation is critical for the development of autonomous vehicles due to the risks involved in real-world testing. While visual aspects of simulators have advanced, generating complex agent behavior remains challenging. Ensuring scenario realism and incorporating preferences for controllable generation are essential for AV training and evaluation. Traditional methods often fail to generate unseen scenarios. RealGen, a novel retrieval-based in-context learning framework, synthesizes new scenarios by combining behaviors from multiple retrieved examples, offering versatile generative capabilities. The RealGen framework introduces a novel approach to generating controllable traffic scenarios. It starts by training a contrastive autoencoder to extract latent representations of scenarios, which are then used for retrieval. This latent representation enables the training of a generative model that can combine retrieved scenarios to create new, realistic scenarios. The key contributions of this work include the development of a contrastive autoencoder, the proposal of the first Retrieval Augmented Generation framework for driving scenarios, and the validation of this framework through both qualitative and quantitative metrics. The framework addresses the challenges of complex interactions, diverse road layouts, and varying traffic regulations, providing a flexible and controllable solution for scenario generation. Figure 1 illustrates the contrast between conventional scenario generation methods and our proposed approach. In A, conventional methods rely on memorizing the data distribution to generate scenarios. Conversely, in B, our method employs a retriever to query datasets, including external data obtained post-training, and utilizes a generative model to synthesize scenarios by integrating information from the retrieved scenarios. This approach enhances the flexibility and controllability of scenario generation, addressing the limitations of traditional methods. Figure 2 illustrates the training and generation pipeline of RealGen, a retrieval augmented generation framework for traffic scenarios. On the left, the training pipeline for the encoders and decoder is shown, where a contrastive loss is applied to behavior embeddings to ensure invariance to absolute positions. In the middle, the training pipeline for the combiner is depicted, utilizing KNN to retrieve scenarios similar to a template scenario and reconstructing the template scenario using the retrieved behaviors. On the right, the generation pipeline is presented, consisting of a retriever and a generator, which together facilitate a two-stage generation process. In traffic modeling and scenario generation, several approaches have been developed. Generative models like ScenarioNet and Waymax use imitation learning trained on large-scale data to create realistic multi-agent scenarios. SceneGen employs LSTM to autoregressively generate trajectories. TrafficSim and TrafficGen focus on learning multi-agent behaviors from real-world data. Adversarial generation methods, such as L2C, use reinforcement learning with collision rate as a reward. MMG enhances realism by incorporating data distribution. ADVSim, ADVDO, and King optimize trajectories using vehicle dynamics. Language condition generation leverages large language models, LLMs. CTG++ replaces gradient guidance with LLM-generated cost functions. LCTGen uses GPT-4 to create heuristic representations, which are then used by a generative model pre-trained on open-source datasets to produce diverse scenarios. The scenario is defined by trajectories tau, which include m-agents over t-time steps, each described by parameters such as position and velocity. The map is represented by lane segments with start and end positions. The scenario autoencoder uses a hierarchical structure with encoders for behavior, map, and initial position, employing spatial temporal transformer layers. To ensure the invariance of the behavior embedding, contrastive learning with InfoNC and Wasserstein distance is applied, resulting in a combined loss function that includes both reconstruction and contrastive losses. The combiner module in this framework takes behavior embeddings from multiple scenarios and outputs a combined embedding. This module is trained using a KNN-based pipeline that forces the model to learn to combine and edit existing scenarios. The training objective is to align the behaviors in the retrieved scenarios with the initial pose and specified map, which aligns with the concept of meta-learning. The generation pipeline consists of retriever and generator components, which are designed to enhance the versatility and efficiency of scenario generation. The experimental setup involves using the new scenes dataset, where each scenario spans 8 seconds at a frequency of 2 Hz. The implementation details include the use of the Atom Optimizer and the Sinkhorn distance, implemented via the geometry loss package. For comparison, several baselines are evaluated, including autoencoder, AE, contrastive AE, and masked AE. The quality of the learned behavior embedding is evaluated through visualizing similar and dissimilar scenarios based on the Wasserstein distance. Quantitative results include the classification of scene ID and the accuracy of linear probing, which demonstrates the effectiveness of the embeddings in capturing behavioral information. The realism of generated scenarios is assessed using metrics such as MMD for velocity, MAID, MFD, SCR, and ORR. The generation performance is compared between reconstruction-based and retrieval-based methods, highlighting the importance of the combiner in RealGen. Additionally, tag-retrieved scenarios are generated and qualitatively evaluated. Safety-critical scenarios are generated using crash templates, and their performance is evaluated in terms of collision rate. Human evaluation through A/B testing shows high preference for RealGen in terms of controllability. For downstream tasks, the generated data is used to augment the training dataset of trajectory prediction models, resulting in improved performance metrics. Figure 3 illustrates the qualitative evaluation of similar and dissimilar scenarios based on our scenario embedding. The rectangles in the figure represent the initial poses of vehicles, while the lines depict their future trajectories. The W2 distance is used as an indicator to measure the similarity between scenarios. This visualization helps validate the effectiveness of our embedding in capturing the behavioral aspects of traffic scenarios. Figure 4 presents 2 key analyses related to behavior embedding and scenario segments. Part A evaluates the accuracy of scene ID classification using different distance metrics applied to behavior embeddings. This helps in understanding how well the behavior information is encoded within the embeddings. Part B displays a Wasserstein distance matrix, which quantifies the dissimilarity between scenario segments. Each block in the matrix corresponds to segments that share the same scene ID, highlighting similarities and differences within a specific time interval. These analyses collectively validate the effectiveness of the behavior embedding method and provide insights into the variability of behaviors within traffic scenarios. Figure 5 presents examples of scenarios generated by RealGen for 6 distinct tags: U-turn, overtaking, left lane change, right lane change, left turn, and right turn. Each example is divided into 2 parts. The left part displays the initial pose and map, while the right part showcases the scenario generated by RealGen. This visual representation highlights the effectiveness of RealGen in creating contextually relevant scenarios based on specific tags. Figure 6 presents examples of crash scenarios generated by RealGen. Each example shows the initial positions of agents, denoted by shadow rectangles, and the resulting crash scenario. The red box in each instance highlights critical elements of the generated scenario, showcasing RealGen's capability to create safety-critical and unseen crash scenarios divergent from training datasets. Table 1 presents the accuracy results of linear probing on behavior embeddings generated by different autoencoder models. The RealGen A model achieved the highest accuracy at 87.8%, outperforming the AE contrastive model with 86.2% and the masked AE model with 67.1%. These results highlight the superior performance of the RealGen model in generating embeddings that are more accurately classified by a linear probe, indicating better representation quality in the context of self-supervised learning. Table 2 presents the results of realism metrics for scenario generation. It compares the mean average displacement error, MAID, and mean final displacement error, MFD, across different methods, indicating the reconstruction performance. Additionally, it evaluates scene-level realism using the scene collision rate, SCR, and off-road rate, OR. The table distinguishes between reconstruction-based and retrieval-based generation methods, highlighting the performance of RealGen AE against baseline methods. This data is crucial for assessing the realism of generated scenarios in traffic simulation. Table 3 presents the results of safety-critical scenario generation methods. RealGen demonstrates superior performance with a collision rate of 0.83, significantly higher than the baseline's RealGen AR, 0.59, and RealGen R, 0.92. This indicates that RealGen is more efficient in generating scenarios with higher likelihood of collisions, showcasing its effectiveness in safety-critical scenario generation. Table 4 presents the results of human evaluation on the controllability of scenarios generated by RealGen compared to a baseline method, LCT-Gen. The evaluation is categorized into 5 driving scenarios: left turn, left lane change, right lane change, and straight. The table shows the percentage of times RealGen was preferred over LCT-Gen and the absolute scores, ranging from 0 to 5, for both methods. RealGen is consistently preferred in all categories, with significantly higher scores compared to LCT-Gen, indicating superior controllability in the generated scenarios. Table 5 presents the downstream task evaluation results for trajectory prediction models. The evaluation focuses on the impact of different datasets on the performance of the Autobot's predictor. The datasets include the original new scenes data, a dataset augmented with Gaussian noise, and a dataset augmented with scenarios generated by RealGen. The key finding is that the model trained with the RealGen dataset achieves the lowest mean average displacement error, MADE, and collision rate, indicating superior performance in trajectory prediction tasks. The RealGen framework introduces a new approach to traffic scenario generation using retrieval augmented generation. Unlike traditional methods, RealGen employs in-context learning to synthesize scenarios by combining and modifying provided examples. This allows for controlled generation of scenarios that can be automatically retrieved from a system requiring only a few template scenarios. The evaluation of the similarity autoencoder model for retrieval and the combiner model for generation shows that RealGen achieves low reconstruction error and high generation quality. However, the current limitation of the method is that the behavior encoder focuses only on agent trajectories, ignoring the complex interactions between agents and lane maps. Improving the feature representation within the behavior encoder could significantly enhance RealGen's ability to generate diverse and controllable traffic scenarios. Thank you for watching.